Alright, today we are going to be proving that the limit as x approaches 0 for sine of x over x, sine of x over x is equal to 1. Now, to do this, we're going to be using something called the squeeze theorem, and I'm going to assume that somebody else is going to be presenting that today, but just in case they aren't, just a quick review of the squeeze theorem. If we have something like x is greater than y is greater than z, and if x equals, let's say x equals q, and z equals q, then y must also equal q, because x is greater than y, and is equal to q, and z is less than y, and it's equal to q, and so there's not a number in between q that's greater than itself and less than itself that equals itself, if that makes any sense. I understand that that's ridiculously confusing, but I think it'll make a lot more sense once we get on and actually apply it practically. Alright, so to start out, we're going to start with this unit circle that I've pre-drawn here. So we're going to label a few parts on it. All right. First, the hypotenuse right here, reaching up until it hits this. Well, the length of that is 1 because it's a unit circle, and the radius of a unit circle is 1. All right. Now the next length we need is the length of this side right here. I'll just make that blue, I guess. Alright, this side right here. Alright. So, the length of that side is sine of x, because any point on a unit circle is the y coordinate on any point on a unit circle is equal to sine of x. So, so this height equals sine of x. Now that we have this, we need to find the area of this triangle. Oh, one more thing. We need the base to find the area. And the base, as you can see, since it's a unit circle, is also equal to 1. Alright, so we're going to take the area of this triangle. I'll do it in green. This triangle right here that I'm outlining. Alright, so the area of that is 1/2 base times height, so that's 1/2 times 1 times sine of x, which equals 1/2 sine of x. Alright. Oh, and let me just do this, and this angle is angle x. Alright, so now we are going to try to find this length right here. I'll do this in kind of a blue-gray. Alright, this right here. Now, so let's think about this logically. In the unit circle, you have angle x, and let's go back to the SOHCAHTOA thing. Tangent is this side equals tangent of x. Just so you know. So tangent is equal to the opposite over the adjacent. So we're trying to find the tangent of x, and that is equal to the opposite side, which is tangent of x, but we don't know that yet, so we're just going to call that opposite over the adjacent, and the adjacent side is 1 because it's a unit circle. So that just means that this 1 can multiply out and become 1 times tangent of x, and so that means that tangent of x equals the opposite side, which is why this is tangent of x. Now, to find the area of this whole triangle, I'll outline it in red. This whole triangle up here and coming down, that is it's just the same procedure. 1/2 times the base, which is 1, times the height, which is tangent of x, which equals 1/2 tangent of x. Correct? let me just make some room here. I'll clear this out. Alright, move this up here. Alright, next what we're going to find, well, I'll move this down here, is what is the area of this little thing here. Oh wait, one more. Alright, what is the area of this little slice of the circle? This segment. I'll try to get this in orange. It's not looking too good, but alright. So this little slice of pizza right there. Alright. So the area of a full unit circle is 2 pi radians. Correct. And since that's only a portion, since we're only trying to find the portion of the circle, we're just trying to find the portion x. So that's x out of 2 radians, 2 pi radians. So that's x over 2 pi. Now, the area of a whole circle is pi times the radius squared, correct? Pi times the radius squared. But since it's a unit circle, the radius equals 1, then the area is just pi. So that's x over 2 pi times pi, and the pi's cancel, leaving us with x over 2. So with that, we're going to set up an inequality and kind of begin the squeeze theorem portion of this. Alright, so we're just going to take our answers here and start with the smallest triangle. So 1/2 sine of x is less than x over 2, which is less than the biggest triangle here, 1/2 tangent of x. Alright, I'm just going to clear all this out. Alright, so now that we've got this inequality, we can start doing some algebra on it. So first, what we're going to do is I'm just going to multiply all of these by 2 to eliminate this 1/2, leaving us with sine of x is less than x is less than tangent of x. Alright, does that make sense? Alright, let me fix this up a little bit. So, anyway. Now, what we're going to do next is, now that we have this, we are going to divide all of these by sine of x. So, let's start here. Divide this by sine of x. Divide x by sine of x. Divide tangent by sine of x. Alright, so what happens? First, these signs cancel, and that just becomes 1, which is still greater than. Now that we're doing this, actually the signs flip. That was my bad. Because as you can see, we're flipping the sign, and the fraction is changing. So 1 is now greater than x over sine of x, and tangent of x over sine of x is actually equal to sine over cosine x, sine x over cosine x over sine of x, and these signs just cancel, and that becomes 1 over cosine x. So we'll just mess with that. Alright, now that we have this inequality here, we are going to see, as you can see, we're very close here. We've got x over sine of x is greater than 1. So what we're going to do now is we are going to multiply by the reciprocal. Alright, so we're just going to basically flip these fractions over. So when we flip 1, that's just 1 over 1, which is still 1, which is still greater than sine of x over x. And when we flip cosine, that's just cosine of x. So now that we have that, I'm just going to make some more room here. Again, just kind of delete this section. Delete this section here. Drag this up. Alright, so now that we have this, we can we're going to start in on the squeeze theorem. Now, the squeeze theorem, like I said before, is if one value is if the outer two values are equal to each other, then the middle value must also equal to that same value. So what we're going to do is we're going to take the limit as x approaches 0 for 1. And since there's absolutely no x variable, that we know that that equals 1. And now the limit as x approaches 0 for cosine x is also equal to 1. And so, because the limit as x approaches 0 for 1 equals 1, and the limit of x approaches 0 for cosine x equals 1, then that means, because of the squeeze theorem, that the limit as x approaches 0 for sine of x over x must also equal to 1. And there you have it. That is the proof that the limit as x approaches 0 for sine of x over x is equal to 1.